Hello students, I am Sachitrakar. Welcome to Cars Physics. This is my lecture 13 on electrostatics and we are continuing electric charge and electric field. Okay. In this lecture, we will discuss on Gauss Law or Gauss theorem. Then let's write first what is statement of Gauss theorem. Okay. According to this theorem or this law, total flux linked with a closed surface enclosing a charge is 1 by epsilon naught times of the magnitude of charge enclosed by the surface. Okay, this is the statement of Gauss law. According to this law, total flux linked with a closed surface. Okay, you may consider any imaginary closed surface. Okay, you may think the shape of closed surface may be spherical, may be cubical, may be cylindrical, or of an irregular shape. Okay, then total flux linked with a closed surface enclosing a charge means there must be charge enclosed by the closed surface. Then total flux linked with the surface is 1 by epsilon naught times of the charge enclosed by the surface. Okay. Then the total flux is represented by phi. Then according to Gauss law, total flux linked with a closed surface is 1 by epsilon naught times of the charge enclosed by the surface. Let total charge means charge enclosed by the surface is Q. Okay. Then proof of Gauss law. See students, Gauss law, before Gauss law, long before Gauss law, Coulomb's laws were found. So it is better to derive Gauss law on the basis of Coulomb's law. Okay. By using Coulomb's law, we can calculate the electrostatic force between 2 point charges. Okay. Again, force experienced by a test charge or force experienced by an unit positive charge is electric field intensity or electric field as we know. So, thus by applying Coulomb's law, we can calculate electric field intensity or electrostatic force between 2 point charges. Similarly, Gauss law has high importance to calculate electric field intensity. The situations in which to calculate electric field by applying Coulomb's law or superposition principle of electrostatic force is made difficult. Those situations are made easier by applying Gauss law. Thus, we can calculate electric field intensity easily in some situations by applying Gauss law than by applying Coulomb's law. Okay, let's prove it first. But before that, we know flux. Flux is a dot product of electric field and area vector. Okay, let's consider any imaginary surface. Any imaginary surface. I have taken an irregular surface. Let's consider this is an elemental area on the surface and this imaginary surface encloses a charge, let Q. Then obviously this will be direction of electric field and this is direction of elemental area means dA. Magnitude of this elemental area is dA and this is direction means the direction of area vector is perpendicular to the plane. I have taken plane of surface like this and this is perpendicular to surface area. Okay. This is direction of the, let angle between them, any angle, let's take theta. Okay. And as we know, flux d phi associated or linked with this elemental area dA is given as dot product of electric field intensity and area vector. Okay. Then d phi is equal to EdA cos theta. Okay. And in accordance with Coulomb's law, if this distance is taken to be r, means distance from point charge to the elemental surface area is r, then electric field at this point considering this point charge is given as k q divided by square of distance k q by r square. Here distance is r into dA cos theta. Again, d phi is equal to k. K is 1 divided by 4 pi epsilon naught q by r square into dA cos theta, and accordingly d phi is equal to q by 4 pi epsilon naught into dA cos theta divided by r square. Okay. In previous lecture, means in lecture 12, we have discussed on solid angle. Again the same advice, dear students who have not gone through lecture 12, please go through lecture 12, and I have tried my best to explain about solid angle. Okay. Then this elemental area dA, let subtends an angle about this point O, let d omega, elemental area dA subtends an angle about point O is d omega. Then as we know, dA cos theta divided by r square is equal to d omega. Okay. Now d phi flux linked with the elemental surface dA is given as q divided by 4 pi epsilon naught dA cos theta by r square. We may take d omega. Then what is total flux linked with the whole surface? Let's integrate both sides. Integration of d phi from 0 to phi. Phi is total flux. Then q divided by 4 pi epsilon naught integration of d omega. Then what will be limit from 0 to 4 pi. And as we have discussed, any closed surface subtends an angle 4 pi, similar as that of sphere. A closed sphere subtends an angle 4 pi about the center, and any closed surface subtends an angle 4 pi. Okay. Then this will be phi q divided by 4 pi epsilon naught, and integration of d omega is omega, and putting the values 4 pi minus 0, upper limit 4 pi, lower limit is 0. Then total flux associated with the whole surface is 4 pi get cancelled, then 1 by epsilon naught times of the charge enclosed. This is proof of Gauss law. So, according to Gauss, total flux associated with an imaginary surface enclosing a charge is 1 by epsilon naught times of the charge enclosed by the surface. This is about Gauss law. And we have already discussed what is the importance of Gauss law. Gauss law has high importance to calculate electric field. Okay. And accordingly we can calculate force. Force is equal to product of charge and electric field. Okay. Means Gauss law makes easier the situations in which Coulomb's law or applying superposition principle of electrostatic force or Coulomb's force are made difficult. Okay. Any imaginary surface, may be spherical, may be cylindrical, may be cubical, or any irregular shape, any imaginary surface enclosing a charge If any imaginary surface encloses a charge, then as we have discussed, if magnitude of charge is q, then total flux linked with the surface is 1 by epsilon naught times of the charge enclosed. This is the point. Any imaginary surface enclosing a charge must be linked with electric flux. So any imaginary surface enclosing a charge is called as Gaussian surface. An imaginary surface enclosing a charge is called as Gaussian surface. So as we have discussed, if a surface encloses a charge, then there must be flux linked with the surface. That surface is called as Gaussian surface. Okay. Then some facts about Gauss law. According to Gauss law, total flux associated with any imaginary surface is 1 by epsilon naught times of the charge enclosed by the body. So if Q means charge enclosed by the body is 0, then obviously flux linked to the body is, or the surface is 0. Okay. Thus, the outcome is like that. If any surface, any imaginary surface, whatever be the shape, any imaginary surface doesn't enclose a charge, doesn't enclose any charge kept in electric field. I am writing the concept and it's very important. Okay. If an imaginary surface doesn't enclose a charge kept in the electric field, may be uniform or non-uniform. Okay. Then flux linked with the surface is 0. And previously we have done integration of d phi is equal to d phi is equal to q by 4 pi epsilon naught into dA cos theta by r square. See students, the limits were 0 to pi, and here you may take surface integration, means for whole surface. Okay. If this angle means dA cos theta by r square is d omega, then for whole surface we are taking surface integral, which will become 4 pi. dA cos theta by r square, surface integration of dA cos theta by r square will be 4 pi, and 4 pi will get cancelled, then flux will come 1 by epsilon naught times of the charge included as per Gauss law. But here we are discussing if any imaginary surface doesn't enclose a charge kept in electric field, maybe uniform electric field or maybe non-uniform electric field, then total flux or flux linked with the surface is 0. And it is seen from the outcome, means formula of Gauss law, means if Q is 0, charge enclosed by the surface is 0, then obviously flux is 0. Then how can we demonstrate it? Okay. Let's consider a known surface, let's consider a cubical body. Okay. This is a cubical body. Okay. Surface is cubical surface. Let each side of the cube is A. Each side of the cube is A. Okay. This cube is kept in, let's consider an uniform electric field. And as we know, an uniform electric field is represented by a number of electric field lines which are parallel and equidistant. This is direction of electric field. Means direction of electric field we have taken along x-axis. Okay. This is along x-axis, this is along y-axis, and this is along z-axis. This is origin. A cubical surface is kept in an uniform electric field. See students, each side of the cube is A. This is along x-axis, this is along y-axis, and this is along z-axis. Let's consider this surface. Then surface area of this surface is A into A square. And direction of this surface area is along x-axis, means A square into I cap. See, this area is held on, this is z-axis, this is y-axis, this area is held on YZ plane. Obviously direction of area vector will be along x-axis, and unit vector along x-axis is I cap, magnitude of area is A square, then area vector is A square I cap directed along x-axis. Similarly, this surface area also has same magnitude, but direction of this surface area is outward, as we have discussed. For a closed surface, direction of each surface area will be outward. Again, magnitude of this area is A square, and this is along negative x-axis, means direction can be represented by taking minus I cap along negative x-axis. See students, this is the top surface area. This surface area is on, this is y-axis, this is z-axis, this surface area is on YZ plane. So obviously, direction of area vector is outward, magnitude is A square. Since this is YZ plane, direction will be along y-axis. Y-axis, this is z-axis, okay. This plane is YZ plane. Sorry. This plane is XZ plane. See, this is along x-axis and this is along z-axis. So this surface is on XZ plane. So obviously direction will be along y-axis, means perpendicular to the surface, and along y-axis we may take unit vector j cap. Similarly, the bottom surface area is directed in outward direction. Again, magnitude of area is A square. If this is along positive y-axis, this is along negative y-axis, means minus j cap. Okay. Then remaining two surface area, the front surface area. Okay. This surface area is on xy plane, and its direction will be obviously along z-axis. This area is A square, and unit vector along z-axis is k cap. Then final surface just behind the front surface. Okay, this surface area is again A square, and direction will be along negative z-axis. This is along positive z-axis, and this is along negative z-axis for backside surface. Then A square j cap and A square minus j cap will get cancelled, but we are considering about electric flux. So electric flux along from this surface, considering this surface, see, this surface, direction of this surface area is along x-axis, and as we know, electric flux is E dot D, okay, or E dot A we may take. So flux from this surface area, from this surface is, electric field is E vector, area vector is A square I cap, both are in same direction, means electric field is given as electric field, magnitude of electric field E, direction along x-axis. So E into I cap dot A square into I cap. So flux is E A square. Okay. Then flux along this, from this space, the total flux will obviously minus E square, since electric field along x-axis and area vector along negative x-axis. So I cap minus I cap means angle is 180 degree, obviously E square, and along this direction, see, direction of electric field is along x-axis and area vector is along y-axis. So flux is EDA cos 90 or EA cos 90, that's equal to 0. Along this direction, in place of 90 degree, here 180 degree and here 0 degree. Okay. Then regarding this surface, the front surface, electric field is E. Electric field is along x-axis and area vector is along z-axis. So again, theta is 90 degree and along from this face, means from front face, flux is 0, and accordingly flux from back face is also 0. Then this is positive, this is positive, this is negative, resulting flux is 0. This is positive, this is negative, resulting flux is 0. Okay. Or you may think, if this is the surface area, top surface area, electric field is parallel to the surface. If electric field is parallel to the surface, then no flux linked with the surface. Similarly, for the bottom surface, electric field is parallel to the surface. For the front surface, electric field is parallel to the surface. For the back surface, electric field is parallel to the surface, means no flux linked for these four surfaces. But for this area, flux is EA square. For this area, flux is minus EA square. So resulting flux linked with the surface is 0. Means if the surface doesn't enclose any charge, then total flux linked with the surface is 0. Okay. Then about Gauss law, total flux associated with a closed surface is 1 by epsilon naught times of the charge enclosed by the surface. Okay. Total flux, very important, total flux, value of total flux independent of shape and size of the surface and the position of charge. Total flux associated with a surface enclosing a charge. Total flux is independent of shape and size of the surface, whatever be the shape and size. As we have discussed, the shape may be square, spherical, cubical, or any irregular shape. Total flux is independent of shape of the surface and also independent of position of the charge. Total flux is always constant. If charge is Q, then total flux is Q divided by epsilon naught or 1 by epsilon naught times of the charge enclosed. Okay. Next important point. For a symmetric body or symmetric surface having n equal faces, symmetric surface having n equal faces containing a charge, let Q, then flux from each surface, flux from each surface is given as phi by n or 1 by n times of the total flux associated with whole surface. If a symmetric body or symmetric surface having n equal faces holding a charge q or containing a charge q in it, then flux from each surface will be 1 by n times of the total flux associated with whole surface. Okay. Let's take an example. Suppose this is a spherical surface. This is a spherical surface, any imaginary spherical surface. Okay. Again on condition charge q at the center, symmetric surface at the center, then flux from each surface is 1 by n times of the total flux. Flux from each face or each face, it will be right. Flux from each face will be 1 by n times of the total flux. Okay. If this is a spherical surface and total charge is assumed to be at the center of the sphere, then total flux is 1 by epsilon naught times of the charge enclosed, total flux. Now let's imagine this sphere is divided into two parts. Charge is at center of the sphere. Then this is a hemisphere, hemispherical surface, and this is also another hemispherical surface. Then total flux is q divided by epsilon naught. Okay. Charge is assumed to be at the center of the sphere. Then flux from each hemisphere, for this hemisphere flux will be q by 2 epsilon naught. For this hemisphere flux will be q by 2 epsilon naught. Because sphere is symmetric. Okay. And flux will be equally distributed for each face. Okay. Then another example. Suppose we are taking a cubical body or cubical surface. Let this cubical surface contains a charge q which is at the center of the cube. Then total flux is q divided by epsilon naught. Then flux from each face will be q divided by 6 epsilon naught. Since q has 6 identical faces, n equal identical faces. So cube has 6 equal identical faces, total charge q is assumed to be at the center of the cube. Then flux from each face of the cube will be 1 by 6 times of the total flux, means q divided by 6 epsilon naught. Okay. Suppose question is asked like this. See student, very important. A cubical surface contains a charge q, but charge is not at the center of the cube. Charge is at one of the corners of the cube. Okay. A cubical surface contains a charge q which is not at the center but at one of the corner of the cube. Then what is total flux associated with whole surfaces of the cube? To have this answer, let's imagine this is a cube upside A. Okay. Keep this type of identical cubical surfaces adjacent to this corner. So we can put 3 identical cubes. Then put 3 identical cubes touching to this corner line. Okay. Then how many cubes become? 4. Then keep another 4 cubes above these 4. This is 1. Then we do keep first sphere, second sphere, and first cubical surface, second cubical surface, and third cubical surface. Then become 4. Then keep another 4 identical cubical surface above them. Then now this charge may be assumed to be at the center. Then we will get 8 cubical surfaces. Then flux from this sphere will be q divided by 8 epsilon naught. Okay, this is our answer. Then we will go to lecture 12 and lecture 14. In lecture 14 we will discuss some applications of Gauss law. Okay, carry on your labor and have concentration in solving numericals. Okay. Thank you, students. Thank you for your support. Thanks.